right, well, we've just gone off and done a couple of simple examples of data abstraction. Now I'm going to do something more complicated. We're going to talk about what it means. And this will be harder because it's always much harder in computer programming to talk about what something means than to go off and do it. But let's go back to almost the very beginning. Let's go back to the point where I said we just assumed that there were procedures makerat and numer and denom. Let's go back to where we had those at the very beginning, constructors and selectors, and went off and defined the rational number arithmetic. And remember I said at that point we were sort of done except for George. Well, but what is it that we'd actually done at that point? What was it that was done? Well, what I want to say is what was done after we'd implemented the operations in terms of these was that we had defined our rational number representation in terms of abstract data. What do I mean by abstract data? Well, the idea is that at that point, when we had our plus rat and our star rat, that any implementation of makerat and numerator and denominator that George supplied us with could be the basis for a rational number representation. Like it wasn't our concern where you divided through to get the greatest common denominator or any of that. Right, so the idea is that what we built is a rational arithmetic system that would sit on top of any representation. So what do I mean by any representation? I mean, certainly it can't be the case that all I mean is George can reach in a bag and pull out 3 arbitrary procedures and say, well, fine, now that's the implementation. Right, that can't be what I mean. Right, what I've got to mean is that there's some way of saying whether 3 procedures are going to be suitable as a basis for a rational number representation. If we think about it, what suitable might mean is I have to assume something like this. I have to say that if x is the result of, say, doing makerat of n and d, then the numerator of x divided by the denominator of x is equal to n over d. See, what that is that's George's contract. What we mean by writing a contract for rational numbers, if you think about it, this is the right thing. And the two ones we showed do the right thing. See, if I'm taking out greatest common divisors, doesn't matter whether I take them out or not, or the place where I take them out, because the idea is I'm going to divide through. But see, this is George's contract. So what we really say to George is what your business is to go off and find us 3 procedures, makerat, numerator, and denominator, that fulfill this contract for any choice of n and d. And that's what we mean by we can use that as the basis for a rational number representation. And other than that, it fulfills this contract. We don't care how he does it. It's not our business. It's below the layer of abstraction. In fact, if we want to say, what is a rational number really? See, what's it really without having to talk about going below the layer of abstraction? What we're forced into saying is a rational number really is sort of this axiom, is 3 procedures, makerat, numerator, and denominator, that satisfy this axiom. So in some sense, abstractly, that's what a rational number is really. Right? So that's sort of easy. That's sort of easy words to listen to, because what you have in your head, of course, is, well, for all this thing about saying that's what a rational number is really, you actually just saw that we built rational numbers. See, what we really did is we built rational numbers on top of pairs. So for all I'm saying, abstractly, we can say a rational number really is just this axiom. You can listen to that comfortably because you're saying, well, yeah, but really it's actually pairs. And I'm just annoying you by trying to be abstract. Well, let me, as an antidote for that, let me do something that I think is really going to terrify you. And it's really going to bring you, face to face with the sort of existential reality of this abstraction that we're talking about. And what I'm going to talk about is what are pairs really? See, what did I tell you about pairs? I tricked you, right? I said that Lisp has this primitive called const that builds pairs. But what did I really tell you about them? If you go back and said, let's look on this slide, all I really told you about pairs is that there happens to be these properties of const, car, and coulter. And all I really said about pairs is that there's a thing called const, and a thing called car, and a thing called coulter. And it is the case that if I build const of xy and take car of it, I get x. And if I build const of xy and get coulter of it, I get y. And that, right, even though I lulled you into thinking that there's something in Lisp that does that, so you pretended you knew what it was. In fact, I didn't tell you any more about pairs than this tells you about rational numbers. It's just some axiom for pairs. Well, to drive that home, let me really scare you and show you what we might build pairs in terms of. And what you're going to see is that we can build rational numbers and line segments and vectors and all of this stuff in terms of pairs. And we're going to see below here that pairs can be built out of nothing at all. Right? Pure abstraction. So let me show you on this slide an implementation of const, car, and coulter. And we'll look at it again in a second, but notice that their procedure definition of const, car, and coulter, you don't see any data in there. What you see is a lambda. Right. So const here is going to return, is a procedure that returns a procedure, just like average stamp. Const of A and B returns a procedure of an argument called pick. And it says, if pick is equal to 1, I'm going to return A. And if pick is equal to 2, I'm going to return B. And that's what const is going to be. Car of a thing x, car of a pair x, is going to be x applied to 1. And notice that makes sense. You may not understand why or how I'm doing such a thing, but at least it makes sense because the thing constructed by const is a procedure, and car applies that to 1. And similarly, coulter applies that thing to 2. Okay, now I claim that this is a representation of const, car, and coulter, and notice there's no data in it. Right? It's built out of air. It's just procedures. Right? There's no data objects at all in that representation. Well, what could that possibly mean? Right? Well, if you really believe this stuff, then you have to believe that in order to show that that's a representation for const, car, and coulter, all I have to do is show that it satisfies the axiom. See, all I should have to convince you of is, for example, that that car of const of 37 and 49 right, is 37, right, for arbitrary values of 37 and 49. Right? See if I really can, and coulter the same way. Right? See if I really can demonstrate to you that that weird procedure definition in terms of air has the property that it satisfies this, then you just have to grant me that that is a possible implementation of const, car, and coulter, on which I can build everything else. Well, let's look at that. And this will be practice in the substitution model. How would I actually Right? How can we check this? We sort of know how to do that. It's just the same substitution model. Right, let's look. We start out and we say, what's car of const of 37 and 49? What do? Const is some procedure. Its value is, const was a procedure of A and B. The thing returned by const is its procedure body with 37 and 49 substituted for the parameters, namely 37 substituted for A and 49 substituted for B. So this expression has the same meaning as this expression. It's car of, and the body of const was this thing that started with lambda, and says, so if pick is equal to 1, where pick is this other argument, if pick is equal to 1, it's 37, that's where A was. And if pick is equal to 2, it's 49. Right, so that's the first step, and I'm just going through mechanical substitution. And remember, at this point in the course, if you're confused about what things mean, go mechanically through the substitution model. Well, what does this reduce to? Carr said, take your argument, which in this case is this, and apply it to 1. That was the definition of Carr. So if I look at Carr, if I do that, the answer is, well, it's that argument, this was the argument to Carr, applied to 1. Well, what does that mean? I take 1 and I substitute it in the body here for this value of pick, which is the name of the argument. And what do I get? Well, I get the thing that says if 1 equals 1, it's 37, and if 1 equals 2, it's 49, so the answer is 37. And similarly, if I'd taken Kutter, that would apply it to 2, and I'd get 49. So you see what I've demonstrated is that that completely weird implementation of const, Carr, and Kutter satisfies the axioms. So it's a perfectly valid way of building, in fact, all of the data objects we're going to see in Lisp. So they all, if you like, can be built on sort of existential nothing. And as far as you know, that's how it works. You couldn't tell. If all you're ever going to do with pairs is construct them with const and look at them with Carr and Kutter, you couldn't possibly tell how this thing works. Now, it might give you a sort of warm feeling inside if I say, well, yeah, in fact, for various reasons, there happens to be a primitive called const, Carr, and Kutter, and if it's too scary, if this kind of stuff is too scary, you don't have to look inside of it. So that might make you feel better. But the point is, it really could work this way. And it wouldn't make any difference to the system at all. So in some sense, we don't need data at all to build these data abstractions, because we can do everything in terms of procedures. Okay, well, why did I terrify you in this way? First, I really want to reinforce this idea of abstraction, that you really can do these things abstractly. Secondly, I want to introduce an idea we're going to see more and more of in this course, which is we're going to blur the line between what's data and what's a procedure. See, in this funny implementation, it turned out that const of something happened to be represented in terms of a procedure, even though we think of it as data. Well, here that's sort of a mathematical trick. But one of the things we'll see is that a lot of the very important programming techniques that we're going to get to sort of depend very crucially on blurring this traditional line between what you consider a procedure and what you consider data. We're going to see more and more of that, especially next time. Okay, questions?
If you asked the system to print A, what would be the result?
The question is what would happen if I asked the system to print A given this representation? You already know the answer. Right? The answer is compound procedure A. Just like last time, let's say compound procedure. Might say a little bit more. Might say compound procedure lambda something or other, depending on details of how I named it, but it's a procedure. And the only reason for that is I haven't told the system anything special about how to print such things. Now, it's in fact true that with the actual implementation of const that happens to be built in the system, it would print something else. It would print, say, this is a pair.
When you define const, and then you pass it in two values, how does it know where to look for the cons? Because you can use cons over and over again. So how does it know where to look to know which A and B it's supposed to pull back out? I don't know if that's expressing that quite right.
Okay, the question is...
Where is it stored?
Okay, the question is, I sort of have a const with a 37 and a 49, and I might make another const with a 1 and a 2, and I might have one called A and I might have one called B. And the question is, how does it know? And why don't they get confused? And that's a very good question. So you have to really believe that the procedures are objects. See, it's sort of like saying, let's try another simpler example. Suppose I ask for the square root of 3. So I ask for the square root of 5. And then I ask for the square root of 20. You're probably not the least bit bothered that I can take square root and apply it to 5, and then I can take square root and apply it to 20. And there's sort of no issue. Gee, doesn't it get confused about whether it's working on 5 or 20? There's no issue about that because you're thinking of a procedure which goes off and does something. Now, in some sense, you're asking me the same question. But it's really bothering you, and it's bothering you for a really good reason. Because when I write that, you're saying, gee, I know sort of a procedure, but it's not a procedure that's just running. It's just sort of a procedure sitting there. And how can it be that sometimes this procedure has 37 and 49, and there might be another one which has 5 and 6 in there, and why don't they get confused? See, so there's something very, very important that's bothering you. And it's really crucial to what's going on. We're suddenly saying that procedures are not just the act of doing something. Procedures are conceptual entities, objects. And if I build consts of 37 and 49, that's a particular procedure that sits there.
And it's different from
consts of 3 and 4. That's another procedure that sits there.
Exists independently.
And exists independently.
And they both can be referenced by Carr and Cooter.
And they both would be referenced by Carr and Cooter. Just like I could increment this and I could increment that. They're objects. And that's sort of where we're going. See, the fact that you're asking the question shows that you're really starting to think about the implications of what's going on. It's the difference between saying a procedure is just the act of doing something, and a procedure is a real object that has existence.
So when the procedure gets built, the actual values are now substituted for A and B. And
That's
then
right.
that procedure exists as a lambda, and
That's
pick
right.
is what's actually passed in.
Yes, when const gets called, and the result of const is a new procedure that's constructed, that new procedure has an argument that's called pick.
But it no longer has an A and B. The A and B are the actual values that were passed in.
And it has, right, according to the substitution model, what it now has is not those arbitrary names A and B. It somehow has that 37 and 49 in there. But you're right, that's a hard thing to think about, and it's different from the way you've been thinking about procedures.
And if I have again const of 37 and 49, it's a different object.
And if you make another const of 37 and 49, you're into a wonderful philosophical problem, which is going to be what the lecture about halfway through this course is about, which is if I const 37 and 49 and I do it again, is that the same thing or is it a different thing? And how could you tell, and when could it possibly matter? And that's like saying that's sort of like saying is that the same thing as this? Or is this the same thing as that? It's the same kind of question, and that's a very, very deep question, and I can't answer it in less than an hour, but we will.